Hello, it's Mailbag today. So no real lesson here, just a chance for you guys to catch your breath. I'm going to ask for some questions. We have four questions to address today. And it just is going to hopefully allow you to see the application of these concepts that we've been talking about so far. Stuff like charges, the flow of current, looking at the concept of voltage. We're going to take a look at how these things apply to everyday things around you. And that is what the mailbag questions have presented us today. So let's get started. We have a question here from Sonali. Hello, Sonali, what do you got for us?
If a common static shock is thousands of volts, why is a shock from a 120 or 220 volt outlet so deadly?
All right. Now, I'm sure everyone at some point has received a shock before. And we're talking about, someone in socks going across the carpet, charging up, and then, they hold the finger away from your skin and you can see like the little light jump between you and the person that's shocking you. Or the classic one is in the classroom in those plastic molded chairs, and you get up from the chair and you go to like the chalkboard or the whiteboard, and then you come into contact with that sort of metal edging or that the chalk rail, and then you get a nice little shock. Or if you've had the chance to use a Van de Graaff generator, and it's the one, that metallic ball, and you can generate a charge, and you get close to it and you can hold your finger just off the surface and you can see the light jump. Either one of those cases, you're talking about thousands of volts. That's what's required to make that actual sort of arc of electricity jump between that surface and to you. You need a lot of voltage for that. And we talked about voltage in terms of the outlets, the 120 volts and the 220 volt outlets that you use for like ovens and what you use for like clothes dryers. Those are deadly. Those outlets, if you were to get a shock from that you could get not only shocked, but simply electrocuted, and it can be fatal. So why is it that a 120 volt outlet or 220 volt outlet can kill you, and yet shocks that have voltages in the thousands do not? Well, it comes down to current and the amount of current that you are receiving. And we are going to take a look at that in the land of Minecraft and going back again, because we're going to use that same analogy, talking about voltage and current, and hopefully it'll make sense. Let's go.
All right, so for this, we need to go back to the world of Minecraft. Hello. All right, we are back here, and I'm going to use the same analogy that we were looking at earlier on, looking at this whole concept of voltage, current, and resistance. We're going to focus in on this one up here. So you can see that, again, for this analogy, the height of these containers that hold all this water represents the potential energy or the voltage of this particular circuit. And the actual flow of water is the current, or is the amount of current in this circuit. So you can see here we have a high voltage and a lot of current. Now, to answer the question, why does something like an electric shock or a shock that you would get from like a Van de Graaff generator, why doesn't that kill you if you're talking about voltage in the thousands? Well, it comes down to current. So what I'm going to do is I'm going to go up. Nope, up. There we go. And you can see we've got the current flowing out there. Now we have a similar thing here, and I want you to see this. There's actually water in this, and the Minecraft physics would say that because you have water, and you can actually see it there, you have drops of water coming down. All right. Now don't forget, that's moving water, so technically speaking, that is current. The only thing is that it's not a lot of current. And if we were to go all the way down to here, we could stand here and get hit with this current and really not get impacted by it too much. We might get a little wet, but that's about it. Now, I want you to understand this. Those are two examples. Both have the same voltage, except this one, if I were to try to stand in this water, I would just get pushed back. Right? You can see I'm actually moving there if I don't start walking into it. I just get pushed out of the way. That's how much energy is in there provided by that current. Whereas here, I can stand here and I'm not getting pushed at all because there's just not enough current. And that's kind of what we're seeing here. Now, to answer the question, well, what about, something like a 120 volt outlet or a 220 volt, I could technically get killed by that. Yes, you could. And that voltage, granted, is a lot lower than the thousands that you're going to get for an electric shock from like a Van de Graaff, or even just from scrubbing your feet along the carpet. What we're seeing up here is a high voltage and very little current, whereas here is a relatively low voltage. Let's say this is the 120 volt outlet, but because there's all this current coming out of it, I have that same problem. Look at the push. I just get pushed right back out of it. So what I'm really trying to get at is that it really is about the current. When we're talking about the danger of getting electrocuted, it's actually the amount of current. If the voltage is high enough that that current can go through you, if there's a lot of current, you could technically get severely hurt or even killed by it. And this is an example here. A relatively low voltage compared to, say, that one up there, but because there's so much current coming out of this thing, this is strong enough to push us out of the way or kill us. And this one, even though it's a high voltage, very little current, and as a result, we actually aren't in danger of getting killed. We might feel it like a shock, but it's not going to kill us or harm us. So I hope that makes sense. And that sort of illustrates that whole concept, or if you hear the phrase current kills, this is what we're trying to show you here. Current does kill. It has that energy to do some damage if the voltage is high enough, but it's the current that you got to worry about. Whereas this, extremely high voltage, but very little current, you might not feel anything, or you might just get a shock. Right, Betty? Yes. You have not left. Oh, trade. Oh, you want to trade. I don't have anything to trade. I'm a dreamer, not a seller.
All right, and Skylar is next. Skylar, what's your question?
Yes. What is a short circuit?
All right, what is a short circuit? This gets back to some of the basic rules around a circuit, and also one of the basic rules around current. First, the current. Current likes to take the path of least resistance. Remember that. And when we get into the circuit, usually, like we said, three things that a circuit will have is a power source, it will have conductors to connect the different things in it, and of course a load or loads, the things that will actually use up the electricity. So a short circuit is a scenario where we have a power source, we have conductors, but we don't have any loads. And as a result, you have current flow that can go all around this completed circuit and nothing to slow it down. That is particularly dangerous.
So in an earlier assignment, I asked you to set up a circuit so that it had no loads in it. And if you did it, you found out that you ended up having this happening. This is just showing you this uncontrolled, or basically this flow of electricity or current without any loads on it to slow it down. And what you end up having is this problem where the power source actually gets really, really hot because of this, simply the amount of current flowing through here and nothing really to slow it down. This is a short circuit. Now, what I want you to see here is that short circuits can also apply to circuit building. And so we have a circuit here, and you can see it's working quite well. And I've got the light bulb sort of converting electrical energy into heat and light, and it's going back to the positive terminal there in the battery. However, if I close this switch or turn it on, you'll notice that now all of a sudden I have generated a short circuit. So this is, again, something that can happen in circuits or in certain parts of a circuit where you create this pathway of no resistance so that current can quickly move around or get back to the positive terminal of the battery, and that is what we call a short circuit.
This clip here is showing you an extreme version of a short circuit. Do not attempt this at home. It is, obviously, you'll see in a sec, it's very dangerous. And this is dealing with just a car battery, a 12-volt car battery. And again, going back to that thing, it's not so much the voltage, but it's the current that can actually harm you here. And you've got a lot of current happening when you see this battery, car battery, undergo a short circuit. Basically, he's just attaching the two terminals together. It's also a reason why you need to be really careful when you are jump starting a car, because if you hook it up incorrectly, it can be dangerous.
All right, and that's pretty good.
Do not attempt this at home. It is a warning, and it is an example of a short circuit. Cole G is next with the question. Cole, what do you have for us?
On a plug, what is the third prong for?
All right. What is this third prong on an outlet? What is it used for? It is called a ground connection, and it is a safety feature that we have for the devices that we plug in. In the event that something goes wrong in the circuitry in your device, so that the electricity that's flowing through the circuit is no longer just flowing through the circuit. In fact, sometimes what ends up happening is those conductors, those wires will break, they'll fray, and sometimes they will actually connect to other parts of your device. Let's say it's a microwave oven, and let's say the high voltage wires in that microwave oven break off or they fray, and they actually have current flowing through other parts of that microwave oven, including the big metal casing around your microwave oven. That could be a problem, especially when you go and touch the microwave oven and you become part of that circuit. This ground is meant to really prevent that from happening, because in the event that you end up having a circuit that that breaks down and you end up having current flowing to other parts of your device, this ground is really meant as an escape route for that current to then flow back out of that device and complete the circuit, instead of having you complete the circuit. This is something that you need to be aware of, so that when you have those plugs in that third prong, and let's say you're trying to plug that device into, let's say, an extension cord that only has two prongs, classic problem. I've seen some people remove that third prong from the plug. Do not do that. That is a safety feature, so that in the event that something goes wrong with the device, there is an escape route or another pathway for current to flow and not flow through you. So does this have something to do with the earth? In a sense, yes. I mean, the reference of ground represents the earth, because the earth has a lot of stuff, matter, and with that, a lot of electrons. That is a possible place where electricity likes to go to complete a circuit. And so that's the reason why we will often call the ground as being someplace where electrons might want to go. It's because they kind of do. And in fact, that's the reason why when you're getting shocked, going back to that example of the Van der Graaf generator, you'll notice that when you're on the Van der Graaf generator, if you separate yourself off the ground, that means if you stand on that platform, and you'll probably notice that the platform is not a really good conductor of electricity, you've disconnected yourself from the ground, which means that you can touch the Van der Graaf generator and you will also get charged. That's the reason why your hair sort of stands up, is because you have this charge building up on you, and it's not able to get down to the ground because you're disconnected from it. You're standing on that platform. That's what we're talking about here. It's that tendency for electrons to want to get to the ground. Now, unfortunately, if you have someone else walking beside you who is actually in contact with the ground and not standing on this platform, you can touch them or they can touch you, and then you will have that transfer of charge, because you are now giving the electrons to that person, and then that person who's connected to the ground will transmit those electrons down to the ground, and they will experience, and you will experience, a shock. So that is, again, just illustrating the fact that, yeah, the ground is a place. The earth is a place where electrons like to go. Current will often like to go there. And that's another thing that we see with current electricity. Logan, it's been a while. Logan, what's your question for us today?
Yes, what is AC and DC?
AC/DC, alternating current, direct current. They are two ways. Those are two ways that we can describe current flow. And the one way to describe alternating current is that it's this back and forth movement of electrons in a conductor. And because it is still moving, that counts as current, even though it is moving one way, then changing direction and moving back, and then changing direction, moving back and back and back and back and back. This movement is still the movement of electrons. So as a result, it counts as current. Now, where would you use this and why do we use this? So if you see those power lines outside of your house and those big towers that you might see along the highway, those all come from power generation plants. And the way that electricity is generated in those power generation plants through generators results in electric current that is alternating. It's this back and forth. And that actually is a nice way of even transporting electricity, because it allows us to transport electricity sort of far distances. So to get it from a power plant to, say, your house. And as a result, you'll notice that the current coming out of your outlets is alternating. It's AC, and it's because where it was generated was from a generator, and generators will produce alternating current. So outlets give us alternating current. Direct current is really current that travels in one direction and only one direction. And actually this is more or less used for a lot of electronics. So electronics like your Chromebook or your phones or your computers, anything that has like a chip or electronics in it, those will use direct current. And that means current going in one direction. What produces that kind of current? Batteries do. Batteries are using something like chemical energy to create this flow of electrons, and that flow is only going to happen in one direction. So that is direct current. But that brings us to this. Yes, this does run off of battery, and so this does have access to direct current, but at some point you have to charge up that battery, or you can run it off of a plug directly. So how does that work? If I've got this computer or laptop hooked up to my plug, the laptop needs DC, the plug gives us AC, how is this going to work? Well, that's the reason why you have these power adapters, things that you'll plug into the wall, and there's usually this big plastic box, or if you have a charger for your phone, you'll notice it's not a simple plug, it's usually like this sort of box that you plug into the outlet. Those are adapters that change AC into DC, because that is what these things need. And that is sort of this interaction between alternating current and direct current. I hope that makes sense. Brandon, end us off here. You've got the last question. What do you got?
Hello, do you know any AC/DC?
Actually, funny you should mention that. I do tend to dabble a little bit in electric guitar. Shall I play something for you? A little AC/DC perhaps? Alright. Ready?